The Cold War's underground cities. In 1959, U.S. Army engineers began constructing a city beneath Greenland's ice sheet. Camp Century, officially presented as a polar research station, served as a prototype for Project Iceworm, a top-secret plan to store 600 nuclear missiles beneath the Arctic ice. The base contained everything needed for long-term habitation: a hospital, chapel, theater, and scientific labs, all connected by tunnels spanning nearly 2 miles. A portable nuclear reactor provided power, while the ice itself acted as natural insulation against -60 degrees Fahrenheit Arctic winters. At its peak, 200 personnel lived comfortably underground, though few knew the base's true strategic purpose. The military abandoned Camp Century in 1967 as shifting ice made the tunnels unstable. Engineers removed the nuclear reactor, but left behind 53,000 gallons of diesel fuel, radioactive coolant water, and assorted hazardous waste, assuming the ice would permanently entomb these materials. That assumption held for decades until NASA's April 2024 aerial survey revealed accelerating melt. Using advanced radar, scientists mapped the base's layout more clearly than ever before. The images show tunnels and structures matching original blueprints, startling evidence of how well preserved this frozen time capsule remains. Project Iceworm was one of the Cold War's most ambitious military projects. The Pentagon envisioned tunneling 52,000 square miles beneath Greenland's ice sheet to conceal nuclear launch sites. Engineers developed rotary snow cutters capable of excavating tunnels at 1 meter per hour and reinforced walls with arched steel supports to withstand ice pressures exceeding 100 tons per square yard. While Camp Century implemented only a fraction of this plan, it proved the concept's feasibility. The tunnels maintained structural integrity despite constant ice movement, but the environmental cost of this innovation is now undeniable. Recent studies suggest Camp Century's site could transition from net snowfall to net melt as early as 2090. Once melting outweighs accumulation, the process becomes irreversible. Scientists estimate 136 acres of buried waste will eventually emerge, including low-level radioactive materials and over 200,000 liters of contaminated wastewater. Unlike Arctic land bases where cleanup is difficult but possible, retrieving materials from Greenland's ice sheet remains technologically unfeasible. Meltwater could carry these wastes into marine ecosystems, creating long-term environmental risks. The 2024 radar data also revealed unexpected subsidence patterns around Camp Century's main tunnels. Some sections collapsed inward, creating sinkholes that accelerate localized melting. This phenomenon, unanticipated in original abandonment plans, suggests environmental impacts could manifest sooner than predicted. The discovery raises broader concerns about other Cold War installations, such as Russia's Neguskoye Air Base or Canada's Dewey monitoring stations, which may face similar fates as permafrost thaws. Camp Century's legacy extends beyond its environmental challenges. Military tunneling technology directly influenced civilian engineering projects. Rotary snow cutters evolved into modern tunnel boring machines used for subways and utility corridors. Insulation techniques developed for Arctic conditions now appear in energy-efficient buildings worldwide. The base also demonstrated that underground spaces could maintain stable temperatures year-round without conventional heating systems, a principle later adapted for Earth-sheltered homes and geothermal facilities. Yet, the base's short operational lifetime, barely 8 years, underscores the fleeting nature of military priorities. Construction consumed 225,000 labor hours, but geopolitical shifts rendered the facility obsolete almost immediately. Intercontinental ballistic missiles eliminated the need for Arctic launch positions, leaving behind a costly, abandoned installation with a complicated legacy. Camp Century's rediscovery highlights the cost of forgotten legacies. Engineers designed the base to withstand decades of ice pressure, but didn't account for climate change. As the Arctic transforms, The site serves as a stark reminder of humanity's impact on even the most remote environments. The shifting ice continues its patient work, revealing the past while below the gleaming skyscrapers of Singapore's Marina Bay. Robotic arms perform maintenance in tunnels most residents never see. These subterranean corridors house the city's critical utilities: power cables, water pipes, fiber optic lines, all monitored by thousands of sensors feeding data to a central operations hub. Singapore's underground utility tunnels showcase smart city technology, where artificial intelligence manages infrastructure with precision human crews can't match. Cities worldwide are adopting IoT sensors to modernize aging water systems. In Philadelphia, acoustic sensors detect the distinct sound of pressurized water escaping pipes, identifying leaks 79% faster than traditional methods and saving 28 million gallons annually. Barcelona's smart water grid uses pressure sensors and AI to predict pipe failures up to 2 weeks in advance, allowing repairs before residents notice disruptions. These systems act like a city's nervous system, sensing and responding to issues before they escalate. Autonomous robots now tackle hazardous underground repairs. Tokyo tested spider-like robots that crawl through sewers, pinpointing cracks with laser scanners. Helsingborg, Sweden, deploys pipe cleaning robots that navigate by memorizing tunnel layouts. Singapore's inspection drones fly preset routes through utility tunnels, using thermal cameras to spot overheating electrical components. These machines reduce human exposure to dangerous confined spaces while delivering consistent, detailed maintenance data. Comprehensive 3D mapping creates digital twins of underground networks. Helsinki integrated data from 18 utility companies into a virtual model, helping planners avoid 2,300 potential conflicts during a tunnel expansion. London maps its 100,000 kilometers of pipes and cables using ground-penetrating radar, with updates streaming to a constantly refreshed 3D model. These maps are like blueprints for a living digital organism, enabling crews to locate shut-off valves quickly during emergencies like gas leaks or water main breaks. However, integrating data across departments remains a challenge. Chicago spent 3 years standardizing formats across 12 agencies before launching its unified underground map. Oslo faced resistance from private telecom companies reluctant to share fiber optic locations. Success depends on clear data-sharing protocols and standardized formats for all subterranean projects. Privacy concerns also arise as surveillance capabilities expand. Singapore's tunnel sensors initially tracked equipment status, but later added worker movement monitoring for safety. Toronto faced backlash when smart water meters revealed individual household usage patterns. To address these issues, cities like Amsterdam anonymize underground sensor data, while Copenhagen allows residents to opt out of certain tracking systems, balancing operational needs with privacy rights. 5G networks are transforming real-time monitoring. Seoul installed millimeter-wave transmitters in sewer tunnels, enabling instant sensor data transmission. London's Elizabeth Line subway uses 5G connected cameras to monitor platform crowding. These high-speed connections allow more sensors to operate simultaneously, critical in dense underground environments where physical access is limited. Predictive analytics are reshaping maintenance strategies. Boston's water department shifted from fixed-interval pipe inspections to AI-directed schedules prioritizing high-risk sections. The system analyzes material age, soil conditions, and repair history to forecast failure points, reducing emergency repairs by 40%. Similarly, Melbourne's underground rail network uses vibration sensors and machine learning to predict track where before costly replacements are needed. Underground digitalization also brings economic benefits. Helsinki leases dark fiber strands in its utility tunnels to telecom companies, generating $3 million annually. Tokyo sells premium access to underground maps for construction planning. These innovations help offset the high upfront costs of smart infrastructure. The true test of these systems comes during crises. When a magnitude 5.4 earthquake struck Osaka in 2021, the city's smart underground network automatically isolated damaged sections while maintaining service elsewhere. These technologies don't just improve efficiency, they save lives when disasters strike. The gender of urban space. At 10 p.m. on a typical weekday, the difference becomes clear. Underground transit stations empty of women first. Surveys show 72% of women feel unsafe using subway systems after dark, compared to just 32% of men. This gap highlights a fundamental design flaw. Urban infrastructure often overlooks the needs of women, with decisions shaped by predominantly male engineers. The consequences are visible in lighting, sound, and layout choices that fail to prioritize safety. Mexico City offers a striking example. Before redesigning the Insurgentes subway station in 2019, women avoided certain corridors entirely due to poor lighting and blind spots where crimes were 3 times more frequent. After brighter LED lights and open sight lines were introduced, female ridership during evening hours rose by 41% in 6 months. Similarly, London's tube stations saw harassment reports drop by 38% after increasing ambient light levels to a consistent standard. These changes transformed spaces once seen as threatening into environments that felt safer and more welcoming. Sound design plays a critical role too. In noisy environments, where background noise exceeds 65 decibels, women report feeling more vulnerable because it's harder to detect approaching footsteps or voices. Berlin tackled this by installing sound-absorbing panels and programming calming tones for late-night hours. Surveys showed a 27% reduction in perceived stress among female riders. These adjustments, though subtle, create a sense of control and calm, much like a protective cocoon. Physical design also shapes behavior. In Seoul, subway cars with dead-end spaces at the far ends discouraged women from sitting there, as these areas were often targeted by harassers. By widening aisles and adding convex mirrors to improve visibility, seat usage evened out across all sections. The cost was minimal, but the impact on comfort and confidence was significant. Similarly, Vienna's segmented seating design, which provides clear personal space boundaries, increased women's likelihood to sit during off-peak hours by 41%, reducing station crowding and improving overall flow. The economic implications of exclusionary design are substantial. Research shows women avoid an average of 1.5 trips per week due to safety concerns. When Vienna introduced gender-sensitive improvements across its U-Bahn network, female ridership during off-peak hours increased by 15% within 2 years, generating millions in additional revenue. These changes don't just benefit women, they create more efficient, inclusive systems for everyone. Some cities now conduct gender audits for infrastructure projects. Barcelona's approach includes ensuring security cameras cover all angles, maintaining clear sight lines, and providing back-to-wall seating in waiting areas. This transforms spaces like Plaza de les Glories into vibrant hubs used equally by all genders after dark. Tokyo's Metropolitan Police addressed another overlooked detail: mirror placement. Poorly positioned mirrors created false blind spots, but relocating them reduced harassment incidents by 23%, a simple, cost-effective fix. Even emergency systems reveal disparities. Traditional call boxes are often placed at heights difficult for shorter users to reach. Stockholm addressed this by adjusting placements based on anthropometric data, improving response times by 14 seconds, critical in emergencies. These examples show that inclusive design isn't just about adding features. It's about rethinking spaces to reflect diverse needs. When New York surveyed female subway riders, their top request wasn't more police. It was wider staircases to prevent bottlenecks where harassment often occurs. Inclusive design transforms underground spaces into safer, more welcoming environments for all. Greenery in the concrete jungle. In Madrid, construction crews recently planted 75,000 trees along a 46-mile ring around the city center, not as a park, but as infrastructure. The Urban Forest Project aims to reduce summer temperatures by 2 degrees Celsius, while absorbing 175,000 tons of CO2 annually. This reflects a growing recognition that green space is critical urban equipment, as essential as roads or sewers. Studies consistently show access to nature provides measurable health benefits. Living within 800 meters of green space correlates with a 30% lower risk of depression. Yet in many cities, economic factors push greenery to the bottom of priority lists, creating stark disparities between neighborhoods. The mental health impacts of urban greenery are well documented. A 2023 study in forests found that all types of green environments improved well-being compared to built-up areas, with water landscapes showing the strongest restorative effects. Participants recovering from stress experienced significantly lower tension levels when exposed to water features. During COVID-19 lockdowns, residents with tree-rich environments near their homes reported better mental health outcomes. These findings highlight how specific elements, like tree canopy density, create stronger benefits than generic lawns or shrubs. Cities generate their own microclimates through the urban heat island effect, where concrete and asphalt absorb and radiate heat. Temperatures in dense urban cores can run 5 to 7 degrees Celsius hotter than surrounding rural areas at night. Green roofs directly counteract this phenomenon. Chicago's City Hall rooftop garden, installed in 2001, maintains surface temperatures up to 30 degrees Celsius cooler than nearby conventional roofs while filtering 9,000 liters of stormwater annually. Singapore has expanded similar projects to over 72 hectares of rooftops, reducing building cooling costs by 15 to 30%. These adaptations lower energy demands citywide while addressing climate challenges. Economic barriers create uneven access to these benefits. A 2019 analysis found low-income neighborhoods averaged 25% less tree canopy than wealthier areas in the same cities. In Washington, D.C., some disadvantaged wards have less than 15% tree cover compared to the citywide average of 37%. This disparity has real health consequences. Limited green space contributes to 20% higher asthma rates in these neighborhoods due to poorer air quality. These areas also experience more severe urban heat effects, compounding health risks during summer months. Some cities are addressing these inequities. Portland, for example, prioritizes tree planting initiatives in heat-vulnerable areas identified through satellite temperature mapping. In Barcelona, the Superblock program creates small neighborhood green pockets, ensuring equitable access across socio-economic groups. These targeted investments help redress historical imbalances in green space distribution. Technological innovations are expanding green space possibilities. Singapore's Gardens by the Bay features super trees, vertical gardens up to 50 meters tall that generate solar power and collect rainwater while hosting thousands of plant species. Milan's Bosco Verticale apartment towers incorporate 900 trees on their facades, equivalent to 2 hectares of forest compressed into building surfaces. These designs demonstrate how cities can integrate greenery even as available land decreases. The evidence leaves little doubt. When cities integrate nature thoughtfully, the payoffs span public health, economics, and environmental sustainability. Whether through street trees, green roofs, or reclaimed waterways, urban infrastructure functions best when it collaborates with nature. As cities grow, ensuring equitable access to these benefits will determine whether urban environments remain livable or become denser concrete jungles.